Have you ever needed a low-cost temporary bridge to cross over a home construction zone, or maybe over a pit of alligators? Today, we're going to design and build a bridge strong enough for me to walk across. And we're going to do it out of cardboard. That's right, cardboard. I'm Shawn Wasserman, and this is Some Assembly Required. I'm filling in for Torben Ruddock today, but I'm going to be just as fun and informative as he was. Let's say a bridge span has to be about 3.5 feet and 18 inches wide, and it's going to have to carry me over this basin of water. The key to bridge design is analyzing the loads involved. In my case, let's say about 200 pounds. That's my weight after beer, pizza, and plus or minus 10% margin of error. The load analysis is very important, considering we're only going to be using cardboard and some tape. Like many bridge designers, we're going to use a triangle shape as the basic building block. Right angle triangles provide the strongest balance of compression, load, and tension. Thanks to the power law, we know that lots of smaller triangles will be stronger than one big one. So I'm going to design this bridge with lots of small right angle triangles. From cardboard like this, it's easy to make them 9 inches by 8.5 by 3.5 inches. With enough of these triangles taped together, we should be able to make a deck strong enough to hold my weight. This cardboard structure is pretty strong. It can hold my weight pretty easily. Let's see what happens if we add some additional weight onto it. Here's me plus 100 pounds. Yup, still holding. I don't have enough weights to do a full destructive test, so let's assume that this bridge can hold up to 300 pounds. When I model the section that I stood on and add a 300-pound force, we see the maximum reaction force at any joint is about 248 pounds. Now I'm going to model the load for the entire bridge deck with supports and a 42-inch span. I'll apply a 200-pound force here in the middle. It looks like the maximum reaction force anywhere on the bridge is under 185 pounds, so I think it will work. Now I need to make what I've modeled. I'll use the same triangles and tape a bunch of them together like this. I'm going to build an extra support to put in the center for our first test. All load analysis says this should hold me. Let's find out. Now let's up the ante and do the real test. Let's see if this bridge is going to carry me across the kiddie pool of doom. I guess 42 inches was a bridge too far. I wonder where I went wrong. I modeled the 200-pound load as two 100-pound forces, one for each foot. But in reality, I put my full 200 pounds on one foot. That reactive force was 255 pounds, which is enough to cause failure. If you're wondering what this program is that I've been using, it's called ForceEffect. It's a free app for Android, iOS, and Chrome that you can get by following the links below this video. Thanks to Autodesk for their help with this video. If you like this video, please give us a like on YouTube, Facebook, or engineering.com. Please tune in next time. We're going to build a trebuchet big enough to fling me over a flaming pit of lava. It's going to be awesome.